Okay, before I start the video, let me preface a few things so the concept isn't lost in a cloud of obscurity. 1. Solar mass. And no, it's not a pastoral gathering of celestial bodies, it's the approximate mass of the sun, because we know that for some reason. It is about 1.989 times 10 to the 30th kilograms, or 2.0 times 10 to the 30th kilograms. To put this number into perspective, this is about twice the size of Sol's dinner. Now that's massive. But all jokes aside, solar mass is used to approximate the amount of matter in other celestial bodies, and is denoted by a capital M and that. Neutron stars will also be highly discussed, as they typically form during the collapse of giant stars and are dim, extremely dense celestial bodies composed primarily of neutrons. They are roughly 10 to 30 kilometers across and can contain as much as 2.2 solar masses. Because of their high density, they have the big gravity and whatnot. Topic number 1, pulsars. The spinny boys of the universe, pulsars are my favorite thing in the night sky. These freaks of nature form when a star condenses but maintains its angular momentum. The moment of inertia on the object sharply decreases due to the sudden change in radius, meaning that its resistance to rotation also drops heavily. This buildup of energy causes the neutron star to spin rapidly while ejecting electromagnetic radiation from its magnetic poles. This radiation can either be X-rays, gamma rays, visible light, or even radio waves, similar to the first pulsar discovered.
In 1967, a postgraduate student at Cambridge University by the name of Jocelyn Burnell was surveying the sky with a newly constructed radio telescope. After a few weeks, she discovered something odd. The telescope had picked up a radio signal that seemed to be pulsating. The pulses had an interval of exactly 1.33 seconds and were initially thought to be nothing more than man-made interference. However, it soon became clear the signal did in fact emanate from deep space, and the unwavering precision of the pulses was unlike anything seen before. As such, many questioned whether it was a naturally occurring phenomenon or a transmission from another civilization. The radio source was even named LGM-1, an acronym for Little Green Men, and Burnell herself could not help but wonder if she'd actually discovered the first sign of life beyond the Earth.
The frequency of the first pulsar discovered, as Lemmino stated, pulsed every 1.33 seconds, and this was initially taken as an alien signal due to its irregularity. Lemmino goes into more detail on his video, and I highly suggest giving it a view for additional information. Another interesting tidbit about pulsars is that their magnetic axes don't always line up with their rotational axes, meaning that projected electromagnetic radiation can be spewed out like a cone instead of just opposite directions across one plane. Compare and contrast these two simulations. One has a lighthouse effect, and the other more of a spotlight effect. Pulsar's electromagnetic ejection is commonly powered by one of three things. 1. Its rotational energy decreases over time in exchange for emission of any type of electromagnetic radiation. 2. Additional matter, accreted from the surroundings, shares its gravitational potential energy with the neutron star, and the mass is channeled to specific X-ray hotspots where it accelerates and strikes the surface at nearly half the speed of light. An extremely high amount of energy is released here, and these areas can get 10 times more luminous than the sun. X-rays are emitted as these spots can get up to tens of millions of degrees. For the final source of energy, electromagnetic radiation can be created through the use of power from the star's magnetic field. Some pulsars are also magnetars, where they have a magnetic field almost quadrillions of times more powerful than Earth's. Pulsars also range in their frequency, based on the mass and angular momentum of the original star. Some pulsars, such as PSR B1937 plus 21, have a rotational period of 1.558 milliseconds. That's over 600 spins per second, And in case you haven't realized, that's hella fast. Say we were to put a hypothetical rock on a hypothetical pulsar with a hypothetical speed and a hypothetical mass. Hypothetically, say the pulsar is 2 solar masses and has a radius of about 10 kilometers. Its period of rotation would be 2 milliseconds. And let's assume the rock is placed perpendicular to the axis of rotation so that it experiences the greatest velocity. Calculate the speed of this rock. So we start by finding the distance traveled around the pulsar. Because the radius is approximately 10 kilometers, we can multiply this by 2 pi and find the circumference. Our period is every 2 milliseconds, so we divide the distance by 0.002 to get the speed in meters per second, which ultimately comes out to 31,416,000 meters per second. How fast is this compared to light? Well, I'm glad you asked. We divide our rock speed by c, which is almost 300 million meters per second, and we have the percentage we are traveling at. This thing is going at nearly 10% the speed of light, while you're jogging at a measly 0.00000001007%. God, you're slow. Now, onto the most confusing thing known to man. No, it's not woman, it's black holes. These are quite literally the densest thing in the universe, other than me, of course. When Einstein theoretically developed the idea of black holes through his equations, they were conceived to have the ability to stop time, possess infinite gravity, and potentially destroy the universe itself, much like Thanos. Einstein initially believed that such a construct could not exist, and boy was he wrong. Well, how do these bad boys even form? They are the result of when an object is crushed beyond its Schwarzschild... Wait, hold on.
Schwarzschild radius.
Yeah, that doesn't help. Essentially, the object in question becomes a black hole when its actual radius is smaller than its calculated Schreiber radius. You can calculate the Earth's radius if it became a black hole by using the equation r equals 2gm divided by c squared, where r is the radius of the black hole, g is the gravitational constant, m is the mass, and c is the speed of light. So if we were to substitute in our constants g and c and plug in the Earth's mass, we wind up with some pretty funky numbers. Using dimensional analysis, we wind up with the radius at 0.00887 meters, or 8.87 millimeters. Just to put this number into perspective, here's the relative size of the Earth as a black hole to a nickel. There's some pretty large black holes out there. We've all heard of Sagittarius A, that weird thing in the middle of our galaxy. SGRA isn't exactly a black hole itself, but it's more the constellation that the black hole is in. This black hole is said to have a radius of about 13,670,000 miles. This radius is maybe a quarter of the way to Mercury. No biggie. But what is a biggie is the black hole located in the quasar cluster of S50014+81. Jesus. This big un has a projected mass of about 40 billion solar masses, and its radius is approximately 47 times the distance from the Sun to Pluto. So I converted the solar mass metric into pounds, and I'm just going to let Microsoft Sam handle this one.
175 decillion 353 decillion 37 decillion 642 million 845 octillion 203 septillion 789 sextillion 103 quintillion 204 quadrillion 567 trillion 895 billion 84,393,549.
Thanks, Sam. You saved me a lot of trouble. Give him a round of applause.
GOMG, we are shot by lasers.
Yeah, Sam, I don't care. Either way, the sky is filled with wondrous and mysterious objects. And these are just 2 examples of some of the oddities available to witness by the telescope. And yet, amongst all the stars, amongst all the chaos, the human race is still alone.